Hello everyone, welcome back to my channel. In this video, we'll be solving a paper 2 question for topic 9, wave phenomena. So this topic is for HL students. So the problem says a painting is protected behind a transparent glass sheet of refractive index N subglass. A coating of thickness W is added to the glass sheet to reduce reflection. The refractive index of the coating N subcoating is such that N subglass is greater than N subcoating is greater than 1. The diagram illustrates rays normally incident on the coating. Incident angles on the diagram are drawn away from the normal for clarity. State the phase shift when a ray is reflected at B. So this problem is specifically tested on thin film interference. So for the thin film interference, we know that the light will experience a phase shift of pi. If the light is being reflected from a high refractive index to a low refractive index, right? So it will experience a phase shift of pi if the light is being reflected from a medium with a higher refractive index to a medium with a lower refractive index. And it will experience a phase shift of 0. So let me write this down. A phase shift of 0. If the light is being reflected from a medium with a lower index to a medium with a high index. So for this problem, the light is reflected at B, which is glass. And we know that the glass has a higher refractive index than the coating. So it belongs to the scenario where the ray will experience a phase shift of pi. So the phase change is pi. Explain the condition for W that eliminate the reflection of a particular wavelength in lambda air. So we want to eliminate the reflection experiences by light in the medium of air. So to eliminate the reflection, what happens is that a destructive interference is required. And when a destructive interference is required, the path difference is equal to m plus a half multiplied by lambda air, where m is equal to any integer. Right? And we also know for thin film interference, the path difference is equal to this part here, 2d multiplied by the refractive index of coating. So we can conclude that the interference here, the path difference here, is equal to 2w multiplied by the refractive index of the coating, which is equal to m plus a half multiplied by lambda air. And this does make sense, right? Because when both boundary experiences the same phase shift, the reflection automatically cancel out. And if you don't see why, you can draw a diagram to see. So let me draw a diagram here. So this is the initial wave pattern. Right, so this is the initial wave pattern. And then what happens is that it experiences a phase change of pi. So it experiences a phase shift of pi. So let me draw another diagram here. So this is the wave pattern here. Actually, let me draw on the same diagram so it looks clear. After experiencing a phase shift of pi. So in order to cancel this reflection, we will need to experience another phase shift that goes back to this black wave right over here, right? So we need to have another reflection, another shift. And this shift here is equal to m plus a half multiplied by lambda air, right? And it does make sense. It does make sense because from here to here is a phase shift of pi over 2. And from here to here, it will be 3 over 2 lambda air. So the generalization formula will be m plus a half multiplied by lambda air. State the Rayleigh criteria for resolution. So the Rayleigh criteria states that the central maximum of one diffraction pattern lies over the first minimum of one diffraction pattern. And when this occurs, the image is just resolved. The painting contains a pattern of bright dots with a spacing of 3 milliliter. Assume the wavelength of Rayleigh is 700 nanometer. The average diameter of the pupil of a human eye is 4 milliliter. Calculate the maximum possible distance at which these red dots are distinguished. So when you see maximum possible distance at which red dots are distinguished, you know that this problem is saying that calculate the distance when these red dots are just resolved. And this automatically links to the problem here, which is the Rayleigh criteria. And we need to know how to represent Rayleigh criteria in terms of mathematical equation. So the equation is this. This is theta, the angular separation. So when the image is just resolved, the theta here is greater or equal to 1.22 multiplied by wavelength divided by the capital D, and this is equal to x divided by d. So what does this symbol represent here? So let me draw a diagram to illustrate this. So for circular diffraction, for Rayleigh criteria, it applies to when there are two light sources. So this is the source 1. This is the source 2. And both of them gonna emit a light. And this is our pupil, which is the slit. and this is the diameter of this aperture. So D here represent the diameter. And this here represent the wavelength. So what happens is they're gonna emit a light. Again, I apologize for my horrible drawing. And here is the distance between two light sources. Distance between two light sources is equal to x. So distance between, so I'm gonna this represent between because I'm too lazy to write out all those words. And here is the maximum distance. So let me actually do it here. So this is the distance, which is represented by this d here. And this quantity is essentially what the problem is asking for. So let's see what we know for this problem. So we know that the diameter, actually let me not erase this. So we know that the diameter is equal to 700 nanometer, which is equal to 7 multiplied by 10 to the power of -9 meter. We also know that a pattern of redox was a spacing of 3 milliliter. So because the redox are light sources, we know that this 3 milliliter here represent the distance between light sources, which refers to x here. So x is equal to 3 milliliter, which is equal to 3 multiply 10 to the power of -3 meter. We know that the average diameter, so the diameter is here, the diameter of the circular aperture is equal to 4 milliliter. Convert that to meter, we multiply by 10 with the power of -3. Right, so this is no information. And essentially the question is asking for the maximum possible distance, which is here, the small d. Oh, sorry, here should be the capital D, the diameter. So what's the distance here? So we can use the equation here. So let me change the color. I want to use right color. 1.22 multiplied by lambda divided by d is equal to capital X divided by d. So d is going to be equal to x divided by 1.22 lambda divided by capital D, which is equal to lambda multiplied by capital D divided by 1.22 lambda here. So let's plug in number. So this is gonna be equal to x is equal to 3 times 10 with the power of -3 multiplied by d, so multiplied by 4 times 10 with the power of -3 divided by wavelength, so 1.22 multiplied by 700 with the power of -9. So this is equal to 14.005 meter, which is equal to 40 meter. So this is the answer for this question, and hopefully this question also gives you a review about what thin film interference is.